Hey everyone, welcome to Talks Tutoring. Hope you're having a great day. Today we are doing question 13b from chapter 7g. So that's your partial fraction chapter. We're going to be doing a lot of questions on that. So if you have any struggles or any doubts with partial fraction, make sure you check out the partial fraction topic video in the link below or in the pop-up above. Right, let's get into the question. Chapter 7g, question 13b, we have to find the definite integral of this function right here. So if you have a look at this function, there's x cubed on top, and then on your denominator you've got two fractions. And you've got two factors, And whenever you have two factors, you have to be thinking about partial fractions. In this case, the partial fraction is a bit weird though. Your numerator power is the same as your denominator power. So one way to go about this is long division. But what you can realize is that x cubed minus 8 is actually the same as x cubed minus 2 cubed, which in this case, if we remember the formula, that's the a cubed minus b cubed, right? If you have a cubed minus b cubed and you factorize it, you can write it as a minus b times by a squared plus ab plus b squared. So that's your perfect cubic formula. In this case, x cubed minus 2 cubed, you can write it as x minus 2. That's x minus a minus b, and then times by x squared plus ab, which is plus 2x, and then plus 2 squared, which is 4. And the thing is, the reason why we did this is that x minus 2 is gonna cancel out with this x minus 2, leaving our work a lot easier. Okay, so root 3, 0. I'm gonna rewrite this. X cubed minus 8 is x minus 2, x squared plus 2x plus 4. Everything divided by x minus 2, x squared plus 1, and then antiderive in terms of x. Okay, the beauty is this x minus 2 and that x minus 2 cancels out, and you're left with only the quadratic, which is a lot nicer than the cubic over this fraction, right? Over this factors. So once again, it's still an improper fraction. You have x squared, the power is 2, the power on the denominator is also 2. If the power is the same, you can't do partial fraction just yet. You have to do the long division, right? So let's long divide this. X squared plus 1. Okay, and then x squared plus 2x plus 4. We are going to divide. X squared multiplied by 1 gets rid of the x squared, and then of course 1 times 1 is just 1. And then we subtract them from each other. X squared minus x squared is 0. That's the purpose of long division. 2x minus 0 is just 2x. 4 minus 1 is plus 3. So what we have, guys, is square root of 3, 0 as your terminals, and then you can write this as 1 plus real remainder, which is 2x plus 3, and then of course divided by your x squared plus 1 dx. Okay, so if you were to divide these, do the long division, you have 1 plus your remainder divided by your quotient. Okay, so what is the next step? Well, we know 1, we can easily antiderive 1. That's fine, it just becomes x. But what about the one here? So you have one function divided by another function. The one on the bottom is x squared plus 1. If I was to let u equals to x squared plus 1, and then I derive that, I'll get 2x. The 2x looks like this 2x, but then there's still this plus 3, right? Which is a bit sticky. You can't just eliminate 2x plus 3. So a clever thing that you can do, guys, is you can split this apart into more fractions. So 1 plus 2x over x squared plus 1, and then plus 3 over x squared plus 1. You can definitely do this, right? It's fine. You can split this fraction apart. Just don't split the x squared plus 1. That always has to remain on your denominator, but you can split the numerator. And you can easily see that this one becomes x, the first term becomes x, the second one is a simple sub technique, and then the third one, it's a numerator, which on your numerator is a number, a constant, divided by x squared plus another constant. What does that look like? Tan inverse. So let's have a look at this. I'm going to split them into three separate integrals so that you can see them clearly over here. Dx. Okay, so now I'm going to start anti-deriving. The best working out I would say is you do the substitution first. Ignore these other two integrands. Just do the substitution because that's slightly the longer working out. So you let u equals to x squared plus 1. Ignore the thing on the side. Just derive it first. Du dx equals to 2x. And therefore dx equals to du over 2x. Now, when you have definite integrals, you need to make sure you change your upper and lower terms as well. So in that case, when x equals to root 3, what is u equals to? If x equals to root 3, u is equals to x squared plus 1, so it's root 3 square plus 1. Root 3 square is 3, 3 plus 1 is 4. And of course, we have x equals to 0 as well, your lower terminal. And in that case, u equals to u square, x squared, which is 0 square, plus 1, and that's just 1. Right, and then you can start writing your integrand once again. Root 3, 0, 1. Yes, I know you can be very tempted to anti-diff this. You can, yes. But I prefer, just for working out, for it to easy to understand, I'll just write it in this form. 4, 1, and then of course my 2x is still there, but then x squared plus 1 becomes a u, and then your dx is now du over 2x. And what happens to the 2x? Well, they cancel out, and that's quite nice. That's the goal of integration, right? Or simple sub. Root 3, 0. Okay, let's do some preparation for the tan inverse in this case. So x squared plus 1 on the denominator, you can't change that. But with the tan inverse, the form that we want it to be in, so if you were to derive tan inverse of x on a, what you get is a over a squared plus x squared, right? So if you were to derive this in terms of x, that's what you get. We want our antiderivative to be in the same form. Unfortunately, the number on top is 3. 3 is not, a squared in this case is 1, so a should be 1 as well, but we have a 3. So what you can do is you can take the 3 out, and then you have a 1 over here, okay? And from that point on, you can antiderive. This easily becomes a tan inverse of x on 1, okay? Right, let's antiderive. What do we have here? If we antiderive 1, we get an x, and then upper terminal root 3, 0. Don't change the x into a u. This is still in terms of x. The only one you change is the second term right here, the second integrand, because you change it to a u, okay? So 1 over u, that's what we're left with. If you antiderive 1 over u, you get log e mod of u, and what we have to do is we sub in 4 and 1, and on the last one, that's 3 times by tan inverse of x on 1, because your a squared is 1, your a is 1, and then we sub in root 3 and 0. Okay, let's sub in some numbers. We sub in root 3, we get root 3, minus we sub in 0, well, we just get 0, and then plus log e mod of, we sub in the 4, that's a 4, and we sub in the 1. Always make sure you put a minus if you're subbing in the lower terminal. So that's minus log e of mod of 1, which is log of 1. And the last one, that's 3 tan inverse of root 3, and then minus 3 tan inverse of 0. Okay, there's a lot of zeros, which is good. You want the zeros. That's, when a question pops up, when your terminal and lower terminals is 0, that's what you like. They cancel out. 0 and 1 are our favorite numbers. Right, root 3, that's there. Log e4, that's still there. The 0 can just disappear. Log e1 cancels out, that becomes 0. Same thing with the 3 tan inverse of 0, that's also a 0. And let's do some quick trig calculation. What is tan inverse of root 3? That is pi on 3. And then let's add some numbers up. Root 3 plus log e of 4 plus pi. Okay, so that's our final answer, guys. This over here is the antidiff, or the definite integral of this function right here. And that's pretty much it for 7G question 13b, guys. Hopefully you found this video useful. If you did, leave a like. I would appreciate that very much. But aside from that, guys, thank you for watching, and I'll see you in the next video.